Hello everyone and welcome back to today's video. So today we'll be doing another tree question, which is to determine the maximum depth of the binary tree. So given a root of a binary tree, we have to return its maximum depth. And the maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf node. So let's take a look at the example right here. So we are given a tree like this. That will mean that this has, as you can tell, this has a height of a level of 1, 2, and 3 respectively. So what this answer requires us to return is the depth of the longest path in a sense. So basically we have to go from 3 to 20, and we can either take 20 to 15 route or 20 to 7 route. So either of them will return us the right answer. But what we cannot do is to go from 3 to 9 and return 2, because that will not be the maximum depth since the answer that we want is 3 right here. So as per usual, when I look at this kind of tree questions, the first thing that comes to my mind is to use the concept of recursion, whereby we keep aiming to solve the smaller and smaller cases to help us build it up to the result that we actually want. So as for all recursion steps, first we have the base case, which is what happens when the things are most trivial. So as you can clearly tell right here, the most trivial case is definitely when we meet something that is none. So if we have something that is none, that will mean that it is not even a node in the first place. So for a base case of none, you simply return 0. Because if it doesn't exist, it simply doesn't have any depth in a sense. However, for the recurring case, what I like to think about when I look at recursive kind of questions is to first examine what happens when we reach the base case and work it out from there. So maybe I'll just take example 1 to explain it again. So as you can tell right here, our base cases are things that are in a sense be lower than all these leaf nodes right here. So this 9, because they will all be pointing at none respectively. Same for the 15 and the 7. So in a sense, all these leaf nodes are they are essentially not our base cases, but once we hit the leaf nodes, we can be sure that our next step will be a base case, since I'll meet the none right there. So I'll return them 0. So can you imagine that, so we can basically tell that at this juncture here, we'll be returning 0. So how do we advance to look at the next step, so the next level? We simply need to add 1 to them, right? So that this at 7 right here, we'll be getting a 1, a 1, and a 1, at this 15 and 9 respectively. So after that, we have to continue to look at the next step. So let's take a look to examine 20 right here. So 20 will already have access to the value, to the outputs returned at the right and left subtree respectively. So what we have to do is to compare and take the maximum of them, since we want to get the next path, right? But in this case, both of them are the same value, so it doesn't matter which one we take. So for 20, we'll be taking either of its child's value, and we'll be adding 1 to it since we are ascending to the next level. So right now, since we have resolved both 9 and 20, we can take a look at the next case, which is 3 right here, which is actually our root node. So 3 right now will have access to the values at 9 and 20, which are 1 and 2 respectively. So as per what I mentioned, how do you tell which values to take in this case? From the left, either from the left or the right subtree. We have to take the maximum of the values right here. So whichever is the maximum, right, then we'll continue to take the output and ascend to the next level. So in this case right here, 1 plus 1, which is 2, is greater than 1. So that will be our maximum value. And as such, we will be taking the output returned by 20, which is 2, and we add 1 to it since you ascended to the next level. Then we'll simply output 3 right here and return it as our value. So as you can tell from the recursive step, what it will look like is we will be checking which one is the maximum from the left or right subtree. And after that, we will add 1 to the output. So that will be what we will return when we are continuing to recurse. So maybe I'll just move on to the coding step so you can get a better idea of what it will look like. So let's move on to the coding step. As you can see, we have the same question right here. So it's always good for us to start with some pseudocode so that we can understand how our general algorithm will flow like. So as mentioned, our base case. So if we meet a none value, so basically it's empty, then we simply return 0 because that's the most trivial case, right, where nothing exists. However, for the recurring step, if supposedly we can continue if a left or right subtree exists, then that will mean that we have to continue recursing to find the value that we want. And we're taking the maximum of the left and right subtree and adding 1 to it since we have to consider the level itself. So how the code will look like is, if root is none, then we can simply return 0. Or else we can return the maximum value that we can get, and we use back the same function for recursion. So we're recursing on the left root and the right root respectively. And after that, we will add 1 to it to consider the level. So it's basically quite a short code. So this is how the code will look like. As for the time and space complexity, I believe that the time complexity will be a big O of n, where n is the size of the tree, because eventually we have to traverse through to all the leaf nodes so that we can guarantee that we can, in the worst case, we have to traverse through all the leaf nodes in order to get our answer. And for the space complexity, if we were to consider the recursion stack, it will be On as well, since we are reaching the leaf nodes of all the tree respectively. So yeah, I guess that's about it. I will just like to add that for your base case right here, right, it's also possible that you can have a base case whereby it's not none, or you can simply treat your base case as the leaf node. And what if you reach here? Like maybe for 20, once you reach 15 and 7, then you can just simply start going back up the tree instead of going down further to the none. But that will mean that for your return step right here, you need to be a bit more careful, because when it's possible that you have a left child that has something but a right child being none. So with that being the case, it's good that then you have to modify the function a bit, because now you can no longer access the root left for a none, because a none doesn't exist a root left, if that makes sense. And yeah, I guess that's about it on my side. The solution does work, and it's relatively, I would say, quite quick as well. So if you have any questions, then feel free to drop in the comments down below, and I'll do my best to answer them. So thanks for watching, and I hope you enjoyed the video.